Hello everyone, I'm Jaegol Chu, one of the instructors of this course. So this is the second lecture in the 14th week, and we will study long short-term memory, which is an advanced and widely used architecture in recurrent neural networks. In this lecture, we will study the motivation for long short-term memory, or in short LSTM, which is an advanced architecture of recurrent neural networks, and how this LSTM works in detail, and also we will briefly go through an alternative architecture called gated recurrent unit, or in short GRU. And LSTM, or long short-term memory, is working as a key component of the modern success in the sequence prediction and generation tasks. And LSTM has the same input and output modules as an RNN. So each RNN cell can be replaced by this LSTM cell. Then the only difference is that it works in a different transformation and functions internally. And then what makes this LSTM so successful compared to the original RNN structure that we learned in the previous lecture? For example, in language modeling and question answering tasks, this long-term dependency can sometimes be a big problem. So the words from long time steps ago are difficult to take into consideration when training to predict the next word. So let's look at this example. And John walked into the room and Jane walked in too, and it was late at night and Jane said hi too. Yeah. So in this case, the answer will be John, which appeared here in our sequence. And from the perspective of backpropagation of the gradient flow, so this was our RNN module, and each time step we give an input as each word. So in this case, instead of using character level language model, we actually used word level language model, but the remaining process will almost the same. And then after giving these sequence of words, and then we want to predict the last word, which is John here in this case, but this information was conveyed in the very first time step. And then let's think about the backpropagation of this gradient. And the gradient will be generated here, and then it has to go through a lot of different time steps. And then each of our RNN cell will transform our gradient value generated from here. And then such transformation is the linear transformation that we had in each module, and also the tan-H nonlinear transformation. And in this case, we have to go through multiple steps of the same linear transformation and the tan-H module, and these gradient of these transformations will be multiplied over and over on the gradient flow that was generated by here. Through our chain rule, this gradient will be multiplied over and over with the same gradient of the same transformation matrix as well as the same tan-H layer, and this results in vanishing or exploding the gradient. So if the gradient was, for example, 3, and then it will keep either multiplied by the same factor, and thus it will either go through the plus or minus infinity, or it can shrink down to almost 0 at the very previous time step. Through the long time sequence towards the end. And now let's look at how this LSTM works in order to solve this problem. So the repeating module or recurrent module in an LSTM contains 4 interacting layers, which is these 4 parts, but overall it takes the input at the current time step and then also another input from the previous time steps hidden state vector and generate current time steps hidden state vector, and then it will be further used to generate the output vector if necessary. And the core idea of this LSTM is that the necessary information can flow through the long time steps without having to be transformed, which can give a distortion, and thus we can handle this long-term dependency effectively. So the LSTM cell maintains some hidden information called the cell state in addition to our hidden state information, and this cell state is the information that generates our cell state, and this hidden state can flow through the next time step without having to be transformed by anything. So in this case, we have a multiplication gate and addition gate, and if we multiply it by 1 and then add it with 0, and then this ct minus 1 and ct will be remaining as the same vector. From the perspective of backpropagation of this gradient flow, the fact that this cell state information can go through multiple time steps without any interruption, which is representing some necessary transformation or distortion, indicates that the gradient can also flow from later time steps through the previous time steps without any distortion or transformation. In that manner, if we supervise at this point, so that the answer should be John, and then this information or error can be propagated without any distortion towards the very first time step. And this kind of architecture is called a skip connection, and this type of skip connection structure has been widely used in many different neural network and deep learning architecture. So for example, the residual net in the context of convolutional neural net has been so successful, and this has this skip connection architecture, so that the information generated from the lower layers can go through multiple layers without any transformation or distortion. And also there is another network called this highway network, which follows almost similar ideas. And let me discuss how this LSTM works in detail. And it takes the same input of the current time steps input vector and the previous time steps hidden state vector, and then these two vectors will be transformed by some linear transformation. And in the original RNN cell, it generated just current time steps hidden state vector, but in the LSTM, it will generate these 4 different sets of vectors, which we call forget and input and gate and output gate. And I will describe each of these vectors in more detail. So the first one, which is a forget gate, is playing a role of determining whether the previous cell information should be forgotten or not. So suppose we have this cell information from the previous time step, and then it is multiplied by the vector called the forget gate, and then this one was the power of output vector that was generated by this linear transformation. And then as we can see, it goes through this sigmoid transformation here, and then the generated vector will have the same dimension as this cell state vector. So if this cell state vector was maybe 3-dimensional vector, for example 3, 5 and -2, and then ft will also be a 3-dimensional vector, but through this sigmoid transformation, the range of the resulting value will all be from 0 to 1, and let's suppose we generated this forget gate vector as 0.7 and 0.3 and 0.4, and then this vector is multiplied with this previous cell state vector in an element-wise manner to generate the resulting vector, and that resulting vector is the output at this point. And as we can see, we are multiplying each element in our cell state vector by a factor that ranges from 0 to 1, and it means the resulting value is containing only the 70% of the original cell state element, and then for this cell state element we are keeping only 30% of information and 40% of the information, and so on. So this vector determines how much we should throw away the information that was contained in the previous cell state vector. The next step is to generate the information that we have to add to the previous cell state information. So given this previous hidden state vector and the current time steps input vector, we go through some linear transformation with some bias and go through this 10H nonlinear layer. So it can be viewed as the step of generating hidden state vector in the original RNN, but this is only the additional information that we have to add to the previous cell state information. But before adding it to the previous cell state information, we go through another transformation by using this input gate, and this input gate is an additional vector that was transformed by its own linear transformation and the bias, and also it goes through the sigmoid layer, and then this vector will range from 0 to 1, similar to this forget gate. And then this input gate, which ranges from 0 to 1 vector, will be multiplied in an element-wise manner with the new information that we generate. And then this information is further added to the previous cell state information after going through this forget gate. And in this process, we finally generate the current cell state information in the current time step. And the reason for using this additional input gate to filter out the cell state information that we currently generated is because the process of generating this current cell state information was done by this relatively simple transformation of this linear transformation and then followed by the 10H layer. And so this information can contain some meaningful information that we want to add to the current cell state information, but at the same time it may have some additional unnecessary information. And so we have to filter out this unnecessary information carefully, and this is done by this input gate in this place. After making this cell state information at the current time step, and then we further generate our hidden state vector, and the process is done by first applying the 10H nonlinear transformation on this cell state vector, and thus this part will have the signal ranging from -1 through 1, and then we can consider this as the hidden state information that we had in the original RNN cell, and it was used for generating the output vector, and then it was transferred to the next time step cell. But before then, we actually have additional step of filtering out some information on generated vector at this point. And this is called the output gate, and this output gate is quite similar to the forget gate or input gate, and it is generated by its own linear transformation matrix and with some bias, and then the resulting vector will go through this sigmoid transformation so that the signal range lying from 0 to 1, and then this 0 to 1 vector will be multiplied in an element-wise manner with this information. So it can hide some information on this part of cell information and to generate the current hidden state vector. In this process, by using this output gate, we can view that the hidden state vector HT selectively contains some information from this cell state information. So we can view this as the cell state information containing the full information that might be necessary to generate the outputs in later sequences, but the current time steps hidden state vector can be used to directly generate the current time steps output. So if we consider the previous example of Jane said hi to John, and then at the last time step we have to generate the output of John, and that information is kept in our cell state information, but in the middle, when generating the other output word in the middle of the sequences, and then they do not need to generate the information about John to generate those output sequences in the middle. Let's look at another architecture called the gated recurrent unit, or in short GRU, which can be used alternatively to this LSTM. And this GRU is a simpler version of LSTM, and the main difference of this GRU is that it now has no difference between hidden state information and the cell state information, but only the hidden state will exist. And in this architecture, this previous hidden state information, which was corresponding to the cell state information in the previous time step, will go through this kind of similar transformation, where we first go through the filtering gate or the forget gate, and then add it further with some additional new information to generate the current hidden state vector. And then now let's go through how the current hidden state information is generated. And then the first one, ZT, can be considered as the input gate. And so using the previous hidden state and the current input vector, we go through some linear transformation and then go through the sigmoid nonlinear transformation, which generates the signal ranging from 0 to 1, which works as some kind of gate or filtering kind of operation. And then we also have another kind of gating information, which we call a reset gate. And then reset gate will go through almost the same process with its own linear transformation parameters. And then this HT of tilde can be considered as the new additional information that we want to add from the current time step. And then, it has this 10H layer to generate the meaningful signal ranging from -1 to 1. And then inside of it, it takes an input of the current input vector at the current time step, and then the previous hidden state vector will be first filtered out by our reset gate. So we throw selectively some information from the previous hidden state vector, and then altogether this information will go through the linear transformation by its own parameter, and then further by this 10H transformation. And finally, this is the information that we want to add to the current hidden state information, but this information is further filtered out by this ZT. So this was corresponding to this input gate in the LSTM. But at the same time, how much to forget the previous hidden state information was done through its own forget gate information, but there is no separate forget gate information here, but the forget gate is actually 1 minus this input gate. So it is called a convex combination here. So the intuition here is that if we want to add like 30% of the current information, and then we have to forget the 70% of the previous information. And that's the intuition behind this convex combination. So in this manner, GRU significantly simplified the process in the LSTM, and the performance shown to be almost comparable to LSTM. So people often use this GRU instead of LSTM. And in summary, we discussed the motivation for long short-term memory, which is a long dependency over time. And then we studied how this LSTM works in detail. And then also we studied this GRU, or gated recurrent unit, also works. And thank you very much.